Now, a lot of math books will teach you how to add fractions before they teach you how to multiply them. But here at Mathantics, we think you should learn the other way around. You remember how easy it is to multiply fractions, right? You just multiply the top numbers together, and you multiply the bottom numbers together, and you have your answer.
Footsteps. I'm just watching Mathantics. You know. Let's see. Wow. The sun is out there. Make sure we're laying in bed. Hey everyone, guys, it's me, Timmy here. And I'm just quiet right now because I'm just resting. And I was looking at my phone and watched some videos of Mathantics. Today, guys, I'm just chilling and I'm just resting because don't worry about it. It's just personal. So, and right now I'm just in the bed right now and I gotta be quiet. So shh. You gotta be really quiet because personal people are down here. So I'm just laying in my bed, look at my phone, and I'm just resting, but don't worry about it, it's personal. So today, guys, I'm going to let you guys to what is happening right now when I show you when I text you the community service. That Mathantics will be back because I'll let you, because I've never seen Mathantics since, you know. I'm gonna show you guys. I'm gonna let you watch Mathantics because I'm taking you to text. So, because I cannot say my personal stuff at my work. I cannot say my personal stuff at my work for Mathantics. So today I'm going to show you guys, Mathantics will be with you, but Mathantics is back. Mathantics is back, guys. And, you know, something you can see here, you know, yeah. So, yeah. So I'm going to tell you what, guys. I'll see you guys another day. See you guys next time before Christmas. Bye, guys.
Hi, I'm Rob. Welcome to Mathantics. In a previous video, we learned that the number line is a helpful tool for showing how numbers relate to each other. It's organized so that numbers increase in value as you move from left to right, and they decrease in value as you move from right to left. In other words, some numbers are greater than other numbers, and the number line provides a quick way to compare them. In math, those sorts of comparisons are called inequalities. Inequality? Why, that's unconstitutional! Oh, hey there. But, don't worry, I'm talking about numbers being unequal, not people. You know, because this is a math video. Ah, I see. Well, this must be the wrong program. I'm really more of a history guy, actually. Well, pardon the interruption. No worries. Anyway, to help you understand what inequalities are, let's first start with a different kind of mathematical comparison called equations. You've heard of equations, right? Equations use a special symbol called the equal sign, like 1 + 1 = 2. This simple equation tells you that if you have 1 and add 1 more to it, the value you get exactly equals 2. So equations tell you when two things have the same value, which means they're equal. Inequalities, on the other hand, tell you when things are not equal. They use two different symbols called the greater than sign and the less than sign. These signs each have a bigger open end that always faces the bigger value, and a smaller pointed end that always points to the smaller value. My teacher used to tell me to imagine that the signs were alligator mouths that always wanted to eat the biggest number. But you may be wondering, why do inequalities get two different symbols when equations only get one? Well, it has to do with the order that we write things in. Take our simple equation, for example. If we switch the order so it reads 2 equals 1 plus 1, that's still true, right? The order didn't make any difference. But what about the inequality 5 is greater than 3? That's true because 5 is more than 3. But what if we switch the order of the numbers like this? Uh-oh. If we do that, we don't have a true statement anymore. We're still using the greater than sign, and 3 is not greater than 5. Notice the open part of the symbol is facing the smaller number, which is wrong. If we want the statement to still be true when we switch the order of the numbers, we also have to switch the symbol to the less than sign. So it reads 3 is less than 5. But did you notice that the less than sign looks just like the greater than sign facing the other direction? That means that you can think of the greater than and less than signs as just one symbol that's read differently depending on which direction it's facing when you read it. If you read it starting from the bigger open end, you say is greater than as you go past it. But if you read it starting from the smaller pointed end, then you say is less than as you go past. The benefit of thinking about the symbols this way, like just one symbol, is that no matter which way it's facing, you won't get confused about the relationship of the things that it's comparing. Oh, and before we move on, I want to show you two other inequality symbols that can be made by combining the greater than and less than signs with the equal sign. But I'm afraid you won't be very impressed by their names. This one is called the greater than or equal to sign, and this one is called the less than or equal to sign. You'll see why these combined symbols are needed in just a minute. For now, we're going to move on and see how basic inequalities look when they're graphed on the number line. Let's start out with the number line and a very simple mathematical statement. N equals 3. Ah, I know what you're thinking. That's got an equal sign, so it's an equation, not an inequality. It's a good observation. And you may also be wondering, what does the letter N mean? Why is there a letter instead of a number? Well, letters are used all the time in math, as you'll learn when you get to basic algebra. They can represent numbers that aren't known yet, or values that can change, or even groups of numbers. In this case, just think of n like a placeholder for a number that's a possible answer. Like n equals 3 just means a number that equals 3. Can you think of a number that equals 3? Yep, it's pretty obvious that the answer is 3. And graphing that on the number line is easy. We just draw a point at 3. But now, what if we change this equation into an inequality using the greater than sign? That would mean a number that's greater than 3. Can you think of an answer for that? Well, 4 would definitely work. If we substitute 4 in place of n, we'd get the inequality 4 is greater than 3, which is a true statement. But there are lots of other numbers that would work also. For example, we could have picked 5 instead, because if we substitute 5 in place of n, we'd get the inequality 5 is greater than 3, which is also true. So inequalities can have multiple answers. In fact, any number located to the right of 3 on the number line would make this inequality true, because values increase as you move to the right. 6 would work, 10 would work, in between numbers like 7.5 would work. No matter which number we choose from the right side of the 3, it will be a valid answer to the inequality n is greater than 3. And notice, the more answers we add to the graph, the more they're starting to look just like a solid line. That's how you graph a simple inequality like this. Since there are an infinite number of possible answers, instead of drawing an infinite number of points, you just draw a line to cover all of those possible answers at the same time. We even put an arrow at the end of that new line to show that it goes on forever, just like the number line itself. Cool, so the graph of the equation n equals 3 is a single point, since there's only one valid answer. But the graph of the inequality n is greater than 3 is a line, since there are infinite possible answers, as long as they are all to the right of 3. Nothing to the left of 3 is a valid answer, because those values are all less than 3. But what about the point located exactly at 3? Would that be a valid answer to this inequality? Well, no, because if we substitute that in, we'd get the statement 3 is greater than 3, which isn't true. Fortunately, mathematicians came up with a clever way to show this on our graph. Instead of putting a solid dot at 3, like you would if it was a valid answer, you put a small hollow dot, or a circle, to show that the value 3 itself is not included in the set of possible answers. Just imagine that the open dot means that the value is missing from the set of answers. But remember those other inequality symbols I showed you? The ones that are combined with the equal sign? If we had the inequality n is greater than or equal to 3, the graph would look almost the same, except that we'd fill in the point at 3 to show that 3 is included in the set of possible answers. In other words, if you want to specifically include the value exactly at the boundary of the inequality, you can use one of the combined signs to include it, so it doesn't feel left out. Think of it like this. Suppose you're 10 years old at an amusement park, and a sign says that you have to be age 10 or older at a particular ride. That could be shown as the inequality, age is greater than or equal to 10. And you'd be in luck because your age, 10, is included in the set of ages that are allowed to go on the ride. But if the sign said you must be older than 10, that would be age is greater than 10, and you wouldn't be able to ride because your exact age is not included. And you would feel sad and angry and so disappointed and a little jealous of your older sister who did get a ride. And you wouldn't even be happy with your ice cream anymore, and you'd want your money back, and you want to just go home by yourself. Okay, let's try another example to make sure you've got the idea. Let's graph the inequality n is less than 7. Just like with the last example, you can probably think of many values of n that would make this statement true. 6 is less than 7, so is 4, so is 1, so is 0. Any number that's to the left of 7 on the number line will work for this inequality because values decrease as you go from right to left on the number line. So again, since there are an infinite number of possible answers, we'll just draw a line to cover all of them. And as before, we'll leave an open dot exactly at 7 to show that point is not included, since 7 is not less than 7. Of course, if we had the inequality n is less than or equal to 7 instead, we'd fill in that point to include 7 in the set of valid answers. Oh, and some of you who are a little ahead in math may realize that there are other numbers that meet the requirements of being less than 7 that are currently not shown on this graph because they're found to the left of 0 on the number line. But don't worry about those negative numbers for now. That's a more advanced topic that we cover in a future video. Making sense so far? Good. Let's move on to something just a bit more interesting. What would happen if we did a little rearranging and combined the two inequalities we just graphed like this? We end up with something new called a double or compound inequality. But what does that mean? Well, this new inequality is defining a relationship between n and two different numbers instead of just one like before. If you read it from left to right, you'd say 3 is less than n, which is less than 7. That's correct, but it's not as clear as it could be. Instead, what if we read this starting from the middle and then read in both directions, one at a time? Reading to the left, we'd say n is greater than 3. Because even though this is the less than sign, we started reading from the bigger open end facing the n. Then, starting from the middle, but reading to the right this time, we'd say and less than 7. In other words, it's asking us what numbers are in between 3 and 7. You can probably think of a lot of numbers that would fit that description, like the number 5. 5 is in between 3 and 7. Like before, we want our graph to include all of the valid answers for this inequality. Since any number that's in between 3 and 7 will work, we'll draw a line from 3 to 7 like this. Then we'll put a hollow dot at each end of that line to show that those numbers aren't included. We got this inequality by combining the first two inequalities we graphed, right? Well, notice that if we put those graphs right next to each other, the section where they overlap is the same as the answer set of our new compound inequality. Pretty cool, huh? And one of the really useful things about compound inequalities is that they're great for specifying a range of values, like a price range. Suppose you want to buy a bicycle. How would you use this idea to specify that you want a bike that's greater than $50 but less than $200? Well, using P to stand for the price, you could write those conditions individually as P is greater than 50 and P is less than 200. But you could also combine them to get this, which means that P is greater than 50 and less than 200. All right, as you can see, inequalities are really useful in math and in everyday life. They help you compare numbers to show which has the greater value, and they help you specify conditions or ranges of acceptable values. Yeah, I guess they aren't as bad as I thought at first. Are you still here? I thought you had another show to do. Yeah, well, it turns out that show got canceled. I'm just here waiting for my Uber to pick me up. Yeah, okay, well, hopefully they'll be here soon, because I'm kinda trying to finish this video. As you've heard me say before, the best way to learn math is to practice. And the best way to learn history is to read a lot about it. All right. As always, thanks for watching Math Antics, and I'll see you next time. Not me, you won't. My ride's here. Learn more at mathantics.com.